So, good afternoon, ladies and gentlemen, or good evening if you've logged in from China or Far East. My name is Matthias Meersmann. I'm the CTO of KHD, and I have the pleasure now to present to you our stepwise approach towards net zero with flexible and efficient solutions from KHD. And I think we're all aware what drives us these days in the cement industry and what this conference is all about. It's all about decarbonization and the challenges that are coming with it. So KHD understands itself to be a supplier of solutions to help the cement producers achieving these targets, and we want to play our role here and be a supplier that is creating value for our customers. And before I get to the subject matter, please allow me some brief words to introduce KHD. This slide shows the path of innovations and the novelties that KHD has brought into this industry. And you can see that since the 1950s, our understanding and our, say, business model was always to innovate and to provide innovations for the production of cement that create real value for the clients. Like, for example, when we introduced the cyclone preheater back in the 1950s, this allowed our clients to cut down their production cost by half. We did the same with the introduction of the flash calciner in the 60s, introduced the first short Pyro rapid rotary kiln on 2 piers in the 80s. I did the same with the roller press in the 80s that allowed very efficient grinding and comminution of raw materials and cement. And as you walk through this timeline towards the right hand side of it, you see that we continued to introduce innovative equipment for the production of cement that helps cement producers achieving their targets. What I'd like to highlight here at this point is the Pyro Rotor as such, which is an alternative fuel reactor allowing for highest substitution rates, being operated with least pre-processed material, coarse material, biogenic material. I'd also like to mention here specifically the Pyro Redox system, which is a calciner extension that allows lowest possible NOx emissions even without catalyst technology. And also what is important in the context of this conference is the flash calciner for calcining clay, which will also play an important role in the future of the decarbonized cement industry. So the message of this picture is that KHD always takes a look at what is the challenge of cement production and try to develop and install process equipment that helps our clients solving their issues and providing value to our clients. Now, let's take a look at the cement industry from a helicopter view. I think we all agree, and that is the message of the conference, that there are challenging times ahead for the cement industry, and we also sense this feeling of urgency. It's time to act now. While production, of course, has to be kept up, which is the primary purpose of the cement industry, of course, we are confronted with a lot of other issues like cost issue, which is a permanent issue, of course, but talking about the environmental footprints, we are challenged also with lowest possible NOx emissions, which are demanded, and the overruling subject of CO2 reduction, decarbonization, is the ruling requirement that we all have to fulfill here. So in order to find out what needs to be done, there have been issued several roadmaps, which more or less tune into identical statements. For example, I am showing here an excerpt from the roadmap of the VDZ, the German Cement Producers Association. They are differentiating two scenarios here, one ambitious reference scenario and one climate neutrality scenario, which is even more ambitious. And if we look at the first two bars here, which relate to the clinker production and the cement production, we see that the VDZ outlines that the thermal efficiency can be increased and must be increased by 13%. Alternative fuel usage should get to 90%, out of which 35% should be biomass. They include hydrogen as a fuel, and they include the use of CCUS technologies in order to be able to reach this climate neutrality scenario. In terms of cement production, they emphasize the focus on CEM2 and CEM4 cements, which means, of course, we have to reduce the clinker factor in the cement down to 53%. And if we take a look at the availability of the usual additions to cement, like ashes or slags, we'll find out that in order to reach this low clinker factor, we will have to come up with other SCMs, supplementary cementitious materials, like, for example, calcined clay. So this also incorporates calcined clay in the final effect on how to achieve this. I always like to refer also to this, say, initial roadmap for the cement industry's decarbonization, which was issued already back in 2018 by the International Energy Agency, which provides 4 basic levers for the reduction of CO2, which is thermal energy efficiency, fuel switching, reduction of clinker in cement, and innovative technologies. And you will find out that these correspond quite nicely to what also the VDZ is proposing. And just last week, the roadmap of the GCCA has been published, and also in that roadmap there is a clear indication and tune in to these statements. So these roadmaps more or less tell the same story, and in order to also provide a view from another angle, and in this case the Chinese angle, it is very interesting to look at what's happening in China, because China as a market is very dynamic, and it is huge, and it is worthwhile looking at what's happening in China. And here we see a very concrete action plan that is being put up by the Chinese government, and there's a program launched that within the next 3 to 5 years they are forced, the Chinese cement producers are forced to make huge progress in all aspects of decarbonization and efficiency. So this action plan defines very concrete targets for energy efficiency and CO2 emission reduction. For example, the program sees that the heat consumption for clinker production should be reduced down to 670 kilocalories per kilogram clinker, while the current national average is about 780. So that is very ambitious. and the Chinese are very serious about this. Also, this program sees that the adoption rate of cement kiln waste heat power generation shall be increased to 90%. So waste heat recovery systems need to be installed in the Chinese cement plants. At the same time, the electrical energy consumption for grinding must be reduced. And the alternative fuel firing rate, the thermal substitution rate, shall become above 15 to 20%, while the current national average is about 7%. The production cost of cement shall also be lowered by the introduction of artificial intelligence and optimized production operation. So zero pollution is at the end of the goals. Zero pollution of the ecological environment for cement production, zero discharge of wastewater and waste from cement plants. By looking at it, we find that there are very precise and concrete targets set upon the Chinese cement industry, and everybody who is looking at the Chinese market can tell that they are really serious about this. And the Chinese cement industry is going to implement what is necessary in order to get there. So the essence of it all is ever more stringent emission limits will be implemented. Technologies to reduce CO2 will comprise maximized utilization of alternative fuels, and they should possibly be waste derived, and they should possibly also be biogenic. Ever more energy efficient production technologies have to be applied. Clinker substitution in cement will call for clay calcination, but it will also call for changes in the grinding technologies because they need to be ever more efficient, and there will also be a demand for ever finer cement grinding to compensate for a lower clinker portion in the cement. And on the long run, and we talk about being commercially available latest by the end of this decade, carbon capture technologies are needed. And I put in brackets here with an exclamation mark, and utilization, because if there is no utilization path, capturing all that carbon wouldn't make much sense. So this is the longer ranging objective for us as the cement industry. But given the complexity of the requirement and the challenge coming with it in all terms, technologically, market-driven, ecologically, logistically, it is clear that we have to apply a stepwise approach in solving these issues. And what I would concentrate on for the next 5 minutes is to show you which first steps can already be initiated today. And I'd like to show you what products KHD can provide to you in order to solve these challenges, to overcome the shortcomings. The first steps today are certainly dealing with maximization of utilization of alternative fuels and possibly also biogenic fuels. The beauty of this is that this is an approach that can at the same time reduce costs and emissions. So it's very logical to concentrate on raising the the TSR rate and to use maximum alternative fuels. Second thing that can be done also today is, of course, reducing clinker factor. And what is also necessary already now is not necessarily to utilize on the wide industrial scale, but we have to start developing low carbon technologies. So what has KHD in its product offering that can help you utilizing that? Why is alternative fuel so difficult to handle. I have to say that in Western Europe, there is already a long tradition in the utilization of alternative fuels. Back in the 1970s, already first cement plants in Germany and Austria started using, for example, used tires or other types of waste fuels. Now, some people think burning waste fuel is an ideal world where you can reduce your fuel costs and do something good for the environment at the same time. Well, basically that is true, but there are some buts coming with it. And these buts relate to operational challenges that come with the combustion of alternative fuel. And the reason for that is that alternative fuels, if there is one definition for alternative fuels, probably this definition is that these fuels have never been intended to be used as fuels, which means their characteristics are not optimized for being used as fuel. And these characteristics mainly consist of their behavior during combustion. And what you see here is the result of an investigation that I've done already 2 years ago, where we looked at the different combustion behavior of typical represents of a mix of alternative fuels. On the left-hand side, you see a very thin foil of plastics. And here you see even still very small particle of higher density plastic. And what you see here is the duration it takes for these samples to ignite and burn out. So you see this very thin foil of plastic ignites with an intense flame very fast, and then is burned out completely after 5 seconds. Still 5 seconds. Maybe you wouldn't have imagined that even for this very small and thin particle, it takes 5 seconds to burn out completely. While if we look at this so-called 3D particle, it takes almost 30 seconds or 35 seconds to burn out. So why is this so important? It is important because in the cement industry, and especially in the calciner, we have combustion in suspension flow. And premature dropout into material will cause problem in clinker quality and also in energy release. So what we learn from this is alternative fuel needs more attention, it needs more retention time, and it needs an optimized reactor in order to burn out. Now, if we look at combustion of alternative fuels in cement plants, it's always this cooperation between pre-processing and co-processing. Pre-processing is preparing this waste material in order to be usable as fuel, and co-processing is the actual burning in the cement kiln. And if we look at this handshake between pre and co-processing, we can clearly identify that the more effort we spend on the pre-processing, the finer and the drier the product gets, the more cost is associated with this. Of course, you'll have to spend lots of effort in separating, sorting, drying, and size reduction. Now, for the co-processing, it's the other way around. If you take high quality alternative fuel material with a high cost of pre-processing, you can just use it in the kiln burner, for example, and you don't have much effort to spend on the co-processing. And the coarser and less prepared the material gets, the more effort you have to spend on co-processing. This leads to two extremes, like, for example, you have a high quality alternative fuel. You don't need much capex for the co-processing, but you need a high cost alternative fuel. Either you have it supplied by your supplier or you produce it yourself. Anyway, the cost and the effort is high. And the other extreme is that you take a low pre-processed material. You don't have to pay much for that material. Sometimes you get money as a gate fee, but you need rather high capex for the co-processing equipment. And in between, you have optimizable situations which can be adapted specifically to the requirements of each and every individual plant in its ecosystem, in its environment. And this is the area where the optimal solutions can be found for each and every plant. This table shows you the range of combustion technologies that KHD is offering in order to fulfill these individual requirements. You can read this table from the left-hand side to the right-hand side with decreasing requirement of pre-processing, meaning that if you have a high-quality fluff, for example, you can use the Pyro Jet kiln burner or the regular calciner technology to utilize these. But if you have low pre-processed material, big size particles, high density particles, or biogenic particles like wood, which is dense, or you have moist materials which require longer retention times, you would use this Pyro Rotor machine, which I will show you in closer detail in a second. Just a quick walk through the, I say, conventional technologies. KHD's kiln burner is called Pyro Jet. It shows some features which are positive and beneficial for the use of alternative fuel like swirl elements and jet nozzles, which also can be operated with oxygen or hydrogen for oxygen enrichment or hydrogen boosting. So this is a rather conventional technology. For the calciner, we also do have several modules which support the combustion of alternative fuel. One easy to flange on module is what we call the Pyro Incinerator. It's a small box that is supplied with air to facilitate ignition and combustion of a certain range of alternative fuels with a certain substitution rate limitation. And of course, like all the other suppliers, we also have this combustion chamber, which is equipped with a real burner at the top, creating an open flame. In that respect, providing optimal ignition conditions for hard to ignite material. Also, this, I have to admit, is a technology that has been around in the industry for quite a while. What I'd like to draw your attention on now is the Pyro Rotor. It's a rotating kiln that is fit onto the kiln riser duct. It's flushed with tertiary air. And this special reactor type was chosen by us because we were looking for the most robust reactor design that is providing most flexibility in terms of retention time, in terms of surface renewal of the material that is always tending to get sticky. If you have a grate combustor with an aerated grate line, there's always a problem of slit clogging and agglomerations building. The Pyro Rotor doesn't have that problem because its constant rotation breaks up these agglomerates and creates new surface for the combustion of the material inside. So there is a lot of advantage in this rotating kiln concept as compared to the great aerated secondary fuel combustion technologies which are available all across the supplier line. The process flow sheet of the Pyro Rotor is shown here. We have the kiln and the kiln inlet chamber with the kiln exit gas running up into the calciner here. We are branching off some of the tertiary air and guide it through the Pyro Rotor. And depending on the rotational speed and the split rate of the tertiary air, we can set different combustion conditions here in the Pyro Rotor, so that we can react on what the specific type of fuel needs in terms of lambda, in terms of temperature, in terms of retention time. Then this exit gas from the Pyro Rotor is mixed in the calciner and can act as a reducing agent for kiln-generated NOx as well. So usually we're fighting NOx with this installation at the same time. This product has been taken up very well in the cement industry. We have now 10 references in total. Out of those 10, 5 are running. Our clients are burning whole tires, tire chips, RDF, plastic waste, mineralic waste, and in China even several hazardous wastes. This table shows some data from real operation. I have compared here what we've guaranteed as to what we've reached in the performance test. And we also investigated the clinker quality. In this case, I've given the data for the clinker-free lime, so that you can see that the separation of combusting alternative fuels not inside the clinker production facility by extracting it into a separate reactor has a lot of benefits. It can get to substitution rates up to 90%. And not jeopardizing with the clinker quality. These clients I've shown here are so satisfied with this reactor that they've ordered, meanwhile, new ones with us, which are under contract execution these days. This slide shows that this Pyro Rotor can be retrofitted into almost any existing plant. And it doesn't require any specific space inside the preheater tower because it will be routed outside the tower anyhow. We can install it inline or perpendicular to the kiln. So we have a lot of flexibility to accommodate each and every individual case. So you see that, especially when we talk about hard to ignite biogenic fuels, or even other fuels which are cost efficient, you need to accommodate retention time and ignition, favorable ignition characteristics, which are being materialized by the Pyro Rotor. This should be good for reaching the highest levels of necessary fuel substitution. Now I'd like to give you a short overview on what we are doing in terms of so-called low carbon technologies. Of course, in low carbon technologies, we mainly talk about Oxy Fuel kilns and carbon capture technologies, which we're working on. We have developed technologies for Oxy Fuel plants, which comprise the adaptation of the kiln burner and especially ceilings to prevent the false air from contaminating the high CO2 concentrated exit gas. And we have developed a clay calcination technology. And if we look at the kaolinite deposits around the world, we see that there are huge deposits available. And as we've heard already this morning, not only pure kaolin is appropriate for clay calcination, but mixtures of clays as well. So clay calcination will definitely play a big role. And therefore we have developed special technology for clay calcination, which is based on only components which we have in our product line already for decades, like cyclones, flash tube calciners, hammer mill. All these components mean nothing new to us, but we've arranged them in a process that allows for efficient drying and comminution, preheating and calcination, and recuperation of the heat by product cooling. In a three-dimensional view, this looks like shown here. We have the drying and comminution, we have the preheating and calcination, and we have the recuperation and product cooling. This all looks like a whole lot of spaghetti, I have to admit, but it's known technology for us. There's no new challenge coming up. Everything we can handle. We can also control the color by a special patented process which controls the oxygen availability and the temperature setting, so that there is this reddish coloring can be avoided, which is detrimental for the cement production. Just to finish my presentation today, I'd like to spend some words on Oxy Fuel. This is a process flow sheet, a general flow sheet of an Oxy Fuel kiln plant, where we have developed the technologies which are needed in order to materialize such a process. And the basic challenge here is to avoid false air from rushing into that gas. That requires specific sealing technologies around the rotary kiln and the other potential in leaking positions. And at the same time, also the burner design has to be adapted in order to provide the identical heat release profile to produce the same quality of clinker, even if you run it with recirculated CO2 instead of air. So that brings me to the end of my presentation. I hope I haven't put too much content into it. I'd like to stress one more thing when closing my presentation. I guess it's clear for everybody to see that the challenges that are ahead of us can only be managed by close cooperation across any kind of separation we had before. Equipment suppliers, cement producers, association, we need to intensify cooperation, and at KHD we are very willing to do so. So I would be looking forward very much to any kind of cooperation and communication I could take up with you. Let's get things done together. Thank you very much.
Hi, Matthias, there are some questions for you in the chat.
Okay, some questions. All right, let me just stop. All right, how do I get to the questions? In the chat. All right, I have one. In your opinion, when do you think, year-wise, Chinese government will reach the 670 kilocalorie per kilogram rate? A good question. The only thing I know about the Chinese market is they are taking these things very seriously. However, this 670 kilocalorie is very challenging, and it will require a lot of optimization. I guess my promise would be at this point they will reach it within the scheduled time frame, which is 3 to 5 years. And then the next question from Thomas Febvre. Very instructive points of alternative fuels, therefore is conceivable to imagine 100% AFR. Let me answer this before I go on with the other questions. 100% AFR is possible only if that AFR contains what we used to call noble fuel, a fuel which is highly dosable, because the product quality in the end needs, at least in the main burner, a certain amount of fuel that is quick to react and quick to control the energy with. So some days before we used to call petcoke an alternative fuel, which is not the case anymore. But you need some fuel which is highly responsive on control changes. Otherwise, I think we have to stop at 90% total AFR. Next question, what impact on cement price? Good question. Nobody can answer that globally. Not only is the cost situation very individual for each and every cement plant, mainly the total boundary conditions are completely different for each and every cement plant in all aspects we are discussing here, be it the price and availability of alternative fuels, be it the accessibility to some infrastructural logistical systems. So that's very hard to answer. Is there like an ideal AFR mix identified? That depends on how you look at it. If you ask a financial guy, he would say the ideal AFR is the lowest possible cost AFR. If you ask the operational and production guys, they say, I need high quality. So ideal, I guess, must be determined by an average cost effect, which not only includes the cost of the AFR itself, but also the kiln up time, that is the availability, the stability of the kiln run throughout the year. So it's a complicated evaluation mechanism, but in the end, the bottom line at the end of the year must be optimized, not only the price of the AFR as such. How do you ignite when 100% AFR? Yes, some AFR does have easy to ignite properties, and by mixing it right, you can still facilitate ignition of the hard to ignite portions with the easy to ignite portion in the mix. So it is possible, but it's specific. Are you using data science to find the perfect balance between characteristics, energy demand, and performance and cost? In that universality as it is explained here, I think it's hard to reach, but we do use data science to optimize our processes, our combustion processes, our kiln operation for each and any specific case. Yes, we do that. I guess that answers your question. Again, another question coming in. We're running so long, so we'll end here. We'll send any further questions. That is not a question, but I will be happy to answer any questions further on in communication by email or whatsoever. Thank you very much.